Move into a new era of learning with Alma Mater.
How are you everyone? Today I'm going to make a video on the internal coding of integers, especially looking at negative numbers. Before I get into the coding of negative numbers, I want to just give you a few definitions of some important terms which you may come across whilst reading any text, and they may be confusing. So I just want to make sure I clear them up to make your reading and studying easier. So I'm going to start with the word encoding. For us to appreciate why encoding is necessary, we have to look at how a computer stores information or data. Now a computer stores its data in binary. In other words, there are a string of zeros and ones. Looking for example, we may have 0, 0, 0, 0. From the work that we have done, this means a number which is equal to like 0. That is, if this one is base 2, this will be 0 in base 10. Using the same approach, we can come across a number like 0, 0, 0, 1 in base 2, and this number would be equal to 1 in base 10. What makes us to know that 0001 is equal to 1 in base 10 is the fact that we are aware we are working with an integer. Now, it's not always that a computer is storing integers or numbers. Sometimes a computer is storing images, sometimes it is storing colors, sometimes it is storing music. That is when this issue of encoding comes in play. So, if a computer is storing numbers, 0001 means 1 in decimal places. If a computer is storing, for example, music, 0001 means something else. So encoding, it gives meaning to whatever binary data we are looking at. We may have encoding that tells us that these are numbers. We may have encoding that tells us that this is music, these are videos, and so forth. You have come across like .pdf, those are documents, .wav, those are, I think that those are songs, and so forth. So that is the importance of encoding. Maybe one last example looking at encoding. Let me say, if you have done some website programming, you may know that 0000 is equal to black. This is color black, you see. So if the encoding tells us that this register is holding a color, then 0000 will mean color black. If the encoding tells us that this register is holding a number, 0000 will mean 0 in decimal places. If it is music, it may be a high-pitched sound, whatever it may be. But encoding gives meaning to a string of binary numbers. I cannot resist giving you another example. Let's say with letters, we have 65. We are going to talk about Unicode and ASCII codes. 65 means letter A. That is, if the encoding is telling us 65 is the register is holding letters, and 65 can also mean the general number 65. So that is the meaning of encoding. Then from encoding, let's look at what is called an overflow. Now a register, let's look at a simple register. A register is a memory location where we store, it's a physical component that stores data. Some registers may be 4-bit registers, some may be, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Some may be 8-bit registers, some may be 16 bits, some may be 32 and 64 bits. Now in this register, it means the maximum binary number that we can store. Remember, a computer can only process binary data. The maximum number that we can store in this register is 1, 1, 1, 1, 1, 1, 1, 1. In other words, we can put 8 ones as the maximum number in an 8-bit register. If it was a 4-bit register, we would put a maximum of 4 ones in that 4-bit register. Now we may run into a common case where our register is smaller than whatever we want to store in there. For example, if we want to store 9 ones in binary, but we have an 8-bit register, then it means we are going to run out of space. We don't know where to put the other one. That is an example of overflow. We are going to look at overflow when we do additions and also when we do binary coded decimals. So I'm not going to explain much on that for now. But this overflow is also linked. I think I've already explained the meaning of the word register. It is also linked to this mystery word which I asked you guys to research on, which is called the word size. The maximum number of bits that a computer can store is referred to as the word size. So the word size can be 16 bits if our register is a 16-bit register. The word size can be 32-bit, 64-bit, 8-bit, 4-bit, depending on the register that we are dealing with. So to explain overflow in terms of word size, if the number or the data that you want to store exceeds the word size of the register, then you will have an overflow. If our register is like 64-bit, we know most computers are 64-bit. If it is 64-bit, then the word size will be 64-bit. Trying to add 65-bit in that register would cause an overflow. In most cases, the overflowing digit is just discarded, but like I said, we are going to look at that a little later. All right. Then another thing is the signed numbers. I explained a little bit on signed numbers in class, but this is just a follow-up. Make sure we have a video where you can come back to and have some reference. When we are talking of numbers, it's very easy when we are talking about positive numbers or integers that we have been talking about in IGCSE. However, the reality is numbers come in positive and negative. So if we have a positive number, it must be known to be positive in all the operations that it is going to be involved. If it is a negative number, it must be known to be negative in all the operations that it is going to be involved in. Now, since our conversions to binary have just been working on the magnitude of the number, for example, we have been looking at 6, convert 6 to binary. We did not address the sign issue. Now there are a number of conventions which are used, or methods which are used to deal with this signed number issue. The easiest to understand is the sign and magnitude convention. It goes like this. I will use a smaller register to make my life a little easier. So I will use a 4-bit register. In other words, the word size is 4 for this register that I've just drawn. The most significant bit in this register is the leftmost bit. So let me say MSB. The most significant bit is the leftmost bit. If it is a 16-bit register, the leftmost bit will be the most significant, and this one is the least significant bit, the LSB. Now, the single most significant bit is going to hold the sign. For example, for positive it would be 1, then the rest will be holding the number itself or the magnitude of the number. So 1001 means the most significant one is positive, then the 001 is the magnitude of the number. So this would be a positive 1. Positive coming from this one and 1 coming from this one. All right. The same will be true for a negative. We would put a 0 here and a negative 1 like that. But this method has got a lot of disadvantages. So most computers tend to use the alternative method, which is called the 2's complement. All right. So the sign and magnitude, I believe that was clear. Let's go to the 2's complement. All right. The 2's complement, the real steps and their explanations to get to the 2's complement can be quite overwhelming if we try to explain them in detail. But the most important part, which is the objective of our syllabus, is to know how to change a number into its 2's complement form, 1's complement form, and stuff like that. I'll talk about the 2 and the 1's complement. So since we are here, let's start with 1's complement. The idea is to get to the 2's complement. All right. 1's complement, according to the definition which I have here in my book, is the binary number obtained by subtracting each digit in the binary number from 1. In other words, if we have 1, okay, I like this color, 1, 0, 0, 1. This is the number, let me call it num. If we want to change this number into its 2's complement, into its 1's complement, sorry, let me say 1 here, I would have to get a binary number by subtracting each digit in a binary number from 1. So if I subtract 1 from 1, this one from 1, I get a 0, 0 from 1, I get a 1, 0 from 1, I get a 1, 1 from 1, I get a 0. So in other words, to get the 1's complement of a number, you simply have to invert the number. If it was a 1, it becomes a 0. If it was a 0, it becomes a 1. That's all you have to do to get the 1's complement. Now, building on that definition of 1's complement, we can now move on to the 2's complement. The 2's complement, according to the definition which I have here, it is the 1's complement of a binary number plus 1. So if we look at this number here, this is the 1's complement of the binary number here. So 2's complement, we get 1's complement and we add 1 to the 1's complement that we have. So with this one, 1's complement would be, okay, we would get, let's see how it works then. We get 1, 1, 1, 1, 0, sorry, 1. That would be the 2's complement of the, that would be the value that we get if we add 1 to the previous 1's complement. All right. Now, the 2's complement issue is quite significant. Let's work with quite a number of examples for us to exhaust or to make sure we have a very good grasp of what is happening in getting the 2's complement. Okay, So I'll give you an example. Let's say we have -1. -1 is our number and we want to get the 2's complement of -1. First, let's get +1. Let's get the binary representation of +1. Once we get the binary representation of +1, we will get the negative by doing the 2's complement steps. Okay, so the binary representation of 1 is, okay, let me make it 110 equal to 0, 0, 0, 1. Okay, let's go to the 1's complement of this number. It is 1, 1, 1, 0, because we simply invert. What was 0 becomes 1, what was 1 becomes 0. Okay, then now we add a 1 to this number. We add a 1 to a 1's complement. So we now have 1, 1, 1, 1. This is the 2's complement of -1. To confirm if this is indeed the 2's complement of -1, you can do this. This is 0 significant bit, 1 significant bit, 2 significant bit, 3 significant bit. The most significant bit in the 2's complement is negative. So if we say 2 to the power of 3 times 1, 2 to the power of 3, 2 from, okay, we said this is the this is a negative, the most significant is a negative, so -2, which is the base, to the power of 3, which is the significance of the bit, times 1, which is this one that we have over here, plus 2 to the power of 2 times 1. Now we are looking at the second one. All these other ones are positive. Plus 2 to the power of 1 times 1 plus 2 to the power of 0 times 1. We will get -8 plus 4 plus 2 plus 1, and that is equal to -1. So you can verify if your 2's complement is correct by using the most significant bit as negative and doing the rest of the steps. Okay, let's do the same for -4. For us to get the 2's complement of -4, let's start with the +4. +4 is equal to 1, okay, no, it's 0, 1, 0, 0. Okay, the 1's complement of the above number is 1, 0, 1, 1. Then adding 1 to the above number, we get 1 plus 1, we get 0 carry 1. 1 plus 1, we get 0 carry 1. Then 1, 1. This is the 2's complement of -4. So -4 is equal to that. This is the right way of getting the 2's complement. But like I said last time, there is an easier and shorter way of doing all these calculations. So let me show you that easier and shorter way. I'm not going to specify what number I am working with, but I'll just use random numbers to show you the steps. So let's start with an easy example. 1 1 0 0. Okay, so let's say this is the positive number. Let's say this is the positive number and we want to get its 2's complement, the positive binary number, and we want to get its 2's complement. We ignore the first zeros and the first 1. Moving from the least significant bit, we ignore the first 0 and the first 1. So this 0, let me change the color. We ignore it, we ignore it, we ignore the first 1. Then after encountering the first 1, we invert everything else. If it was a 1, it becomes a 0. If it was a 0, it becomes a 1. So this one becomes 0. This is the 2's complement of this number. Let's do another example. Let's say we have 44. We want to find the 2's complement or the binary representation of minus 44. First step, let's change positive 44 to binary. Okay, that would be quite a long step. 2 into 44, we get 22 remainder 0. 2 into 22, we get 11 remainder 0. 2 into 11, we get 5 remainder 1. 2 into 5, we get 2 remainder 1. 2 into 2, we get 1 remainder 0. 2 into 1, we get 0 remainder 1. So 44 is equal to, we read from the bottom going up, it's equal to 1 0 1 1 0 0. I hope I did not make any mistake in that conversion. Now we want to get the binary representation of minus 44. In other words, we want to get the 2's complement of this number. So okay, all right, so this number, we're coming from the least significant bit. We ignore the zeros and everything until we encounter the first 1, which we also ignore. So 0, keep it as it is, keep it as it is. The 1, we keep it as it is. Everything else, we invert it. So this becomes 0 1 0, something like that. So you don't change anything until you encounter the first 1 coming from the least significant bit. Then the first 1, you ignore it, but after that first 1, you invert everything else. So minus 44 would be like that. 1 2 3 4 5 6. Okay, I need to add 2 more zeros just to make sure that it is an 8-bit register. We only have 4-bit, 8-bit, 16-bit, 32-bit, 64-bit, 128-bit, 2 whatever bit. They don't come in anything else other than the powers of 2. Okay, so this is the 2's complement, and I hope you will be able to convert many more numbers into 2's complement. Okay, so